Now, we all know what CO2 is, and we know that we breathe it out, sure. But have you ever thought about, well, how is it that that CO2 gets back to the lungs? It's done so one of three ways. It's either diffused inside the plasma in the blood, it's bound to the hemoglobin, or it's converted to a buffer. Now, it's this buffer that I want to talk about. It's what we call the bicarb buffering system. And a lot of the time, when I start to draw it out, students get a little bit overwhelmed. And I think that's for very good reason. It is a little bit scary at first, but I'm going to try to break this down. So what we've got here is CO2. When it binds with water, you have to remember that water is inside the blood. Think about the plasma content of the blood. That makes up 55%, which means that 55% of the blood, theoretically, is water. So when CO2 is inside the blood, it binds with the plasma. And it forms something what we call carbonic acid. But that carbonic acid is a very weak acid, which means that it breaks down again and it converts to what we call HCO3, which is bicarb, and of course the hydrogen. Now, every time you see the bicarb buffering system, I want you to write it out like this. Okay, so what we've got on the left-hand side, CO2, of course, is referring to the lungs. So it's what we call respiratory. Now, everything on the right-hand side here is metabolic. Now, you can think of that because of the bicarb that's involved on the right-hand side of this equation. Now, a very general rule of thumb here to apply is that anything that occurs on the left-hand side also occurs on the right-hand side. So if I increase the amount of CO2, it increases the amount of water in which it binds, therefore forming more carbonic acid, therefore dissociating into more bicarb, and of course, more hydrogen. Now, it's this hydrogen that's the key player in the bicarb buffering system, because when we start talking about pH, and if it's going up or down, or if we've got respiratory acidosis or metabolic alkalosis, it's going to depend on pH. That's the big takeaway here. So think about the hydrogen. Is it up? Is it down? And how do we get that? Well, I've just said, if I increase CO2, I increase hydrogen on the other side. Brilliant. Now, what you need to keep in mind is if I increase hydrogen, I decrease pH. It's always, I like to think, inversely proportional, right? Kind of like a seesaw. One goes up, the other one goes down, especially in the case of pH. So if I increase CO2, I increase hydrogen, therefore I decrease pH. We know that it's on the respiratory side, so it must be respiratory acidosis. Brilliant. Respiratory acidosis. Why is it acidosis? Well, think about it. The pH is down, right? It's a decrease, and if it's down, I like to think that's acidic acid spill on the floor. It's low, okay? So this is what we call respiratory acidosis. Now, the opposite that's going to occur here is respiratory alkalosis. Think about it. If I decrease CO2, if I just get rid of this here, if I decrease CO2, there we go. Decrease CO2, I'm going to decrease hydrogen and therefore increase pH. And if I increase pH, it's more alkalinic, so therefore it must be respiratory alkalosis. Very straightforward. Okay, a similar principle is going to apply when we're looking at metabolic, but it's a little bit more confusing, but bear with me. Every time you're looking at the right-hand side here, the metabolic component of this equation, I want you to think that the HCO3, the bicarb, I want you to think of it as being a mop. Yes, a mop, right? Now the hydrogen, remember, I want you to think of it as being a spill, right? If I get a bigger mop, I can clean up more spill. If I decrease the size of the mop, I take up less spill, okay? So if I increase the mop, HCO3, right? What am I going to do? Well, I'm going to decrease the size of the spill, of course, right? Because I can clean more up, which means that I increase pH. And if I increase pH, that's alkalinic. So this is what we call metabolic alkalosis, right? And things start to make sense. Again, remember, the opposite's going to occur in the case of acidosis. If I decrease the size of the mop, right, I increase the size of the spill because I can't mop it up. Therefore, remember, what I do to one, the opposite occurs. I decrease pH, and this is what we call metabolic acidosis. See if you can use that.